This here is a rather small example of a Joseph Newman motor, the energy machine of Joseph Newman. Very large, very powerful neodymium magnets rotating in there. They are 70 millimeters by 40 millimeters, and there's two of them sandwiched around a 10 millimeter drive shaft. That shaft has a 20 millimeter coupler, which is driving a Fisher & Paykel smart drive motor generator. That generator is currently putting out, coincidentally, a nice round number, 110 volts, through this 25 watt, 240 volt globe. The ammeter is showing almost nothing, but then it should, because its scale is not appropriate for this application, unfortunately. What we have driving this machine is a H-bridge circuit. It's all electronically driven, unlike the historical versions, which are all commutator driven. The circuitry is being driven at 14 volts, which is a 4017 decade counter oscillator, into a standard H-bridge, and the power supplies for the base of all those transistors are from here, and a few diodes to negate the backflow, which is very critical to prevent implosion. Currently the input voltage is a whisker under 500 volts, and the needle is touching 40 milliamps. Of course, that's not accurate because the duty cycle is not 100%, so it's actually less than 40 milliamps. The duty cycle has just been increased. I'm going to have a look at the scope shot and then turn the motor off and explain the duty cycle. What we've got here, as you can see, are square wave pulses driving this coil, single coil, two wires coming out of it, in a traditional induction method. The H-bridge is putting positive voltage, negative voltage, positive voltage, negative voltage across the coil to make it rotate, and the magnets will chase. These little peaks you see at the bottom of the square wave are AC induction, what you would recognize as a typical sine wave. However, it's not a sine wave because the sine wave aspect of it is covered up by the square waves. But what I'm saying is this magnet is producing a sine wave which is running underneath the square wave and reducing the power input. So I'm able to run this motor, and the motor, to a large degree, is able to power itself. And this clearly shows up in the input voltage. If I was to power this coil without the magnet in it, it would consume about 200 milliamps. If I rotate with a magnet in there, if I let the magnet rotate, it will generate the field, and the coil's input will drop from 200 milliamps to, as you can see, as much as 40, but actually as little as 2 or 3 milliamps. If I take the load off the generator, off the motor rather, the input power will drop hugely. And that is the operating principle of the Newman motor. So what you want is a motor with a small load on it, and then it's almost free to run. So you want a large motor. The next one I build will be much larger, about 3 times the size. Therefore, it will produce a lot more torque at a low RPM. And that large amount of torque will cost almost zero electrical input. The motor from this torque is 0.2 of a watt or less, and it is extremely powerful. If it were possible to burn your hands by holding a shaft at low RPMs, then it would do that, because at 0.2 of a watt it is impossible to hold the shaft. So what you want for a Newman motor is like the great man himself did, was build one on the back of a trailer, extremely large and extremely ludicrous looking for a motor, but then in the pursuit of free energy, it's not often going to look dignified. But what we can do is produce a high-power motor with a very small power input, as long as you sacrifice size. And that is how it works. You use existing principles, use existing electrical principles that are clearly understood and explainable to anyone with a degree, and they will concede that this is a very unusual machine that doesn't break any of the laws. Highly conventional. So, there we have it. Have a good day, build your own, it's good fun, and make a bit of free electricity in the process. See you back for the big one.